Hello and welcome to the 7th and penultimate Markup UK 2020 webinar. We have heralded its arrival by devoting 6 of our sessions to XProc 3.0. In our previous session, we heard Liam Quinn's insights into XSLT 3.0. Prior to that, David Maus also spoke about Schematron. But today is the turn of XQuery. My name is Andrew Sales, one of the Markup UK organisers. I'll be hosting this webinar. XQuery is the Plumber's Toolkit, given by Adam Retter. Before we begin, some housekeeping announcements. Please use the Q&A section to post questions. My co-hosts Ari and Geert will monitor these, and we will have some time at the end to put them to Adam. A quick reminder that this webinar is being recorded and we will make it available on our YouTube channel later today. See the links for this and the previous sessions on our website, markupuk.org. Our presenter, Adam, is the developer of FusionDB, one of the lead developers of ExistDB, the man behind REST-XQ, and an acknowledged expert on XQuery. So without further ado, please, Adam, take it away.
Hello, everybody. Thank you very much, Andrew. Welcome to my webinar on XQuery Plumber's Toolkit. I'm just going to start sharing my screen, so hopefully you can see my slides. And I need to stop the video, I'm told, so let's see if I can stop the video. Okay, hopefully you can all see these slides. So without further ado, let's get going. Okay, so you probably all know who I am by now, I hope. If you don't, Andrew's done a pretty good introduction, or there's a slide here. The slides are online, so you can refer back to this later if you wish. So there's been a lot of talk about XProc, but what I'm wondering is, what did we do before XProc came along? And if we were doing that before XProc, do we actually need XProc? So I did a little bit of research. I've used all of these standards. XPL is XML pipeline language, which is quite related to the Orbion XForms software, but it was also submitted to the W3C as an option for a pipeline language. Now, ultimately, it didn't make it, and XProc was born. But there's a few options and things that we did before XProc was around. So in 2006, when my XML career kind of started, we were looking around for doing some work with XML, and we wanted to write pipelines, basically. So we looked at XPL, but because it was Orbion only, we felt that that wasn't really a good choice. We didn't want to be tied to Orbion. And at the same time, there was a piece of software called Apache Cocoon, but it was very Java-y based. And we wanted to sort of not have to write lots of Java code. We also felt that at that time, Cocoon was perhaps dying. However, I looked it up yesterday and I see that it's still alive and it's been reinvented. And I don't know what its status is, but it's had a release fairly recently. So at that time, we wrote our processing pipelines in XQuery. We had lots of XQueries. We had XQueries calling XQueries calling XQueries, and XQueries calling XSLTs that called XQueries. But basically, the driver was XQuery with lots of XQuery modules and some XSLT modules as well. And from that, we would produce either HTML, PDFs, or XQuery updates. So this was back in 2006, and it kind of gave me the feeling that everyone's talking about XProc, but I can already do everything maybe that XProc does. And I can do it in XQuery. I don't really need a lot more. But is that really true? So I had to think about it for this talk, and I sort of felt that XQuery was, as I titled the talk, the Plumber's Toolkit. Has lots of tools, and it allows you to plug all of these things together to create these kind of pipes that you need. But I think the real power of XQuery often comes from the implementation. So depending on which processor you use for running your XQuery, depends on which vendor extensions are available and what you can do with it. The good news is that most processors have a huge amount of extensions, and many of them are standardized across the processors via either XPath or XQuery. So I thought we would set a challenge for today. Now, this challenge uses data about COVID-19. Now, I realize that's not the happiest of subjects, and I apologize if this is offensive to anyone. I don't mean it to be. But the good news from my perspective is there's lots and lots of data available about COVID-19. So we can ask interesting questions and do interesting things with these data sets. Now, today we're going to focus on the first question of this challenge, strictly because of the amount of time that we have. And I also want to make it clear that I'm not a data scientist, I'm a software engineer. So some of these statistics that we produce may be somewhat questionable. But I want to answer the question, is there a proportionate relationship between COVID-19 mortalities and relief funding that's being provided for COVID-19? So how might we go about that? So we're going to use XQuery because that's the point of my talk. We don't necessarily need XProc. And we can use XQuery to integrate all of the things. So we're going to take not just XML data, because it's obvious that you can work with XML data with XQuery, but we're going to take lots of data from different places. We're going to work with some graph data. We're going to work with some relational tabular data. We're going to access this stuff over the web. And when we've got it, all our data, we're going to write some queries and we're going to produce a report. And for today, our report will be a HTML web page. Okay, so let's see how we might do that. To answer the challenges, of course, we need some data. So I went looking for data, and the type of data that we need to answer these questions are statistics, obviously on COVID-19 deaths and relief funding, related medical research journal articles. That's really for the second question I posed, which was to try and work out if there's more medical research happening in the places where there's more COVID-19 mortalities. And then some of these data sets don't connect to each other directly. So we need to be able to map some of the data from one to another. For example, some of them use state names. This data is all USA based, I should say, so USA states. And some of them use state abbreviations. But if we want to join on the location, i.e. the US state, we need to use either names or abbreviations. So we need to be able to map between the data sets. Okay. So first of all, I went looking for medical research journal articles. Now, the obvious place for US data to get this is National Library of Medicine, particularly a data set that many of you are probably familiar with called PubMed. This data set holds abstracts of journal articles. They have a nice web API, and you can retrieve the data in XML. The only problem is that you can only retrieve 10,000 records at a time. And when I did a search for COVID, I found 210,000 records. And how will I get this data? Well, surprisingly, I decided to use XQuery. So I wrote an XQuery that uses an extension module from the XPath project for doing HTTP requests so we can access the data from the web. I then call the search API provided by PubMed to get a list of results. That gives me my 210,000 results. Because I can only retrieve results at 10,000 at a time, I then have to call the fetch API multiple times to get all 210,000 results. Once I have my XML results, I then store them into the XML database using an XQuery module called XMLDB, which is an extension. And now we'll have a look at the XQuery that I wrote to do this, and we can see how it works. So let's look at some real code. So I'm running FusionDB here, but I'm using the Exist database admin client to interact with it for people that are familiar with Exist. And all of the code that I've written is 100% compatible with ExistDB. So you can run this, all of the examples today, either on FusionDB or ExistDB. And actually there's very little code that's specific to Exist. So you can run it mostly on any XQuery implementation with a few minor changes. Okay, So the first query we're going to look at is the one for downloading the PubMed data. So let's pull that up. Okay. Now, if you're not familiar with XQuery, you'll just have to trust me on what I'm telling you here. What we basically do is we declare a few variables at the top of our XQuery script for the API. So this is the URL of the PubMed API. This is how we perform a search, the endpoint, the web endpoint for performing a search, and this is the one for fetching. And we're going to store all this data into our database, and we're going to put it in a collection called PubMed data. Okay, so how does this work? Well, an XQuery always starts at the bottom after all of the declarations. We have a number of functions, and then at the bottom we have our main part of our query. So the first thing I do is I set up a database collection to hold our data. All this really does is create an empty collection in the database. So we use the XML DB module to make sure the collection isn't available, not collection available. And if it isn't available, we create a new collection. Okay, so a collection is like a folder on your computer, so you have somewhere to store your data. Okay, now we have our collection set up. We run our search function, search articles with our keyword COVID. This is the term that we're going to search the PubMed database with. So let's have a quick look at our search articles function. Now this is up near the top. So this is our search articles function. It takes our keyword and it's going to return a document containing an e-search result. Now an e-search result is the XML that comes back from the API. This is quite a simple function. We build the URI for accessing the PubMed API. And then we use the XPath HTTP function to send a HTTP request. And it's a GET, and we just do a GET on the URI that we've built. This is error checking here. It just makes sure that the request has given us a valid response and then gives us back the data from the API. This is very, very simple. Okay, but with just this tiny little bit of XQuery, we've made a request to a foreign API on the web and retrieved some XML data. So that's not a bad start. So once we have our search results, we need to fetch our articles. Now, between the search API and the fetch API, you have to pass the result. So we pass in the details of our result that was required by their API. The fetch articles is a little bit different from the search because we can only fetch 10,000 articles at a time. So we have to do multiple calls to the API. So let's have a quick look at the fetch articles. Okay, so this is the fetch articles. We don't need to worry too much about these two. These are just API keys that we had to pass. And then there's a count. Now the count is the total number of articles that we want to retrieve. In our case, this will be about 210,000 because that's the number of results for COVID. What we then do is we need to calculate how many pages of 10,000 results we're going to fetch. So we have a little function, calculate page starts. We tell it that we've got about 210,000 results. And this was a variable that we declared earlier that says the maximum we can fetch is 10,000 per page. So our calculate page starts, which is just above here. It's quite a simple function. You divide the total by the page size, do some calculations, and this is just a little bit of math, and it gives you the start number of each page. So the first page will start at 1, the second page will start at 10,001, the third page will start at 20,001, and each page will be full of 10,000 results each. Okay. We then build the URI, one for each page start, so that we can get the start of each page, and we send the request just as we did before. And this function returns all of the results because of this loop. So it loops around this section, returning all of our PubMed articles. Okay, great. So once we have our articles, we basically do a very small loop where we pull out the ID from each article, purely for the version of giving the document that we store a name. So we store each article in its own document, and we use the XML-DB module, this is an extension, to store the article into our collection with the name based on the ID. So I'm not going to run this query right now because retrieving 210,000 documents over the web and storing them takes about 8 minutes, and I don't have a spare 8 minutes. But I did run this earlier today, so I can show you exactly what we have. So let me close this. So we have our PubMed data here, and let me just pull a document from our PubMed data so you can see what one of these looks like. Okay, so the query that I just wrote accesses our PubMed data collection where we stored all our PubMed documents, and the one tells it that I just want the first document. It doesn't matter what it is, I just want the first document. And then at the bottom here, you can see our PubMed article. This one is from the Medical Journal of Australia, and it has this title. It's about tracking and mitigating the impact of COVID-19. And we can tell who published it, the authors, and a bit more information about it, when it was published, where it was published, and various other bits. So that's one article. Now we have 210,000 of these stored in our database. Okay, so I'm going to switch back to the slides. So we now have our PubMed data set of research articles about COVID. Okay, and we need some other data sets as well. So we want to take some statistics on COVID-19 deaths. Now, the best place to get these in the US appears to be the Centers for Disease Control and Prevention, CDC. And they provide an API that we can use to get those as well. Unfortunately, their data is made available in CSV format. It's not in XML. It's comma-separated value, so it's tabular data. So what we'll do is we'll write an XQuery again, because it's all about XQuery today. And we'll use the same HTTP module, very, very similar. We'll call the download API for the CDC. It's a slightly different API, but the principle is the same. And that will give us our CSV data. And as far as XQuery is concerned, this is really just a string. It doesn't really know what CSV is. So we'll then parse that string of CSV data into an array according to the XQuery data model, so that we can work with the CSV data in XQuery. Once we have the CSV data, we'll do some cleanup because their data isn't necessarily perfect or in the format that we want. And then we'll use another XQuery extension module. This one is for structured query language, SQL. And what we're going to do with this data is, rather than storing it into our XML database, we're going to store it into a relational database called MariaDB. So I also have MariaDB running here. And we'll use our XQuery to generate our SQL statements to create our SQL table and insert the rows all into MariaDB. So let's take a look at how we do that. So I'll open up my query. This one. So we'll start at the bottom where the main part of our query is. So the first thing we're going to do is download the CSV. And we've got some funny looking identifier here. So we'll have a quick look at the download CSV function. Okay, here's our download CSV function. So the funny string that we passed is the data set ID. What that really is, it's just the identifier for the data set that we want to pull from the CDC. And just like before, you can see that we have a URI declared here for the CDC API. Before we were using PubMed, but this one's a little bit different for CDC. But the principle is the same. We build a URI of the request we want to make. We send the request. We check for errors. And if there are no errors, we return our data. And this time, our data is coming back as a string because it's comma-separated value data. We don't really know what it is. It's just a big string of data. Okay. So We call download CSV, and we've got our string data, which is our CSV. And then we want to actually make some sense of this. So we call parse CSV. Now, there are various libraries and modules out there for parsing CSV, but it's actually relatively trivial to do. So I just wrote my own function here. But by all means, you can use something that already exists and is probably a bit more battle tested than what I have here. But let's have a quick look, because it's not particularly complicated if I find it. So here's our parse CSV function. We simply tokenize the string, so we split it on line endings. So we have lines of text rather than one big line of text. And then for each row, a line in a comma separated value is a row. So for each row, we parse the row. Okay. And parsing the row is very, very simple. We simply use analyze string with a regular expression. And what this does is it takes a row or a line from a CSV file and it splits it into multiple columns. And it does so respecting things like quotes and commas and things like that. So even if some of the data has quotes around it or commas in it, we should still get the right thing. This regular expression is quite simple, but it does seem to work. And then once we've got it back, we just do a little bit of tidy up. We replace a couple of things. And then we have basically an array. So the array holds all of the columns in our row. And because this function is called once for each row, we end up with lots of arrays, one array per row of CSV data. Okay. So once we've parsed our CSV data, we want to store it in our SQL database. And this is the interesting part, really. So let's see how we do that. So we have this little function that we wrote, store as SQL table. We pass in our CSV data. This is a sequence of arrays where each array is a line from the CSV file. And very simply, just use the SQL extension module. So we create a connection to the database. We defined how that looks a little bit earlier. I'll just show you that quickly. So we're going to use the MariaDB, because we're using the MariaDB database, the MariaDB driver. We want to connect the MariaDB server running on my local machine. And we're going to connect as the root user. I haven't set up proper users for the database because this is just a small demo. But these are the credentials for connecting to MariaDB. Okay, so we connect to the database, and then we execute a query to create or replace a database within the database server, I should say. So this connects to the database server. And then we create a database, which is just a place to keep our data, a little bit like we created a collection earlier. Once we've created our database, we need to create a table to hold our data. And we have a little function that reads the first line of the CSV. So reads the first row and generates a create table SQL statement. So somewhere up here, create table. So we loop through the columns because each row is an array, loop through the columns, and we make sure the column name is safe for using in SQL. We replace some special characters, and we determine the data type for the column. And we basically are building a little string here. Well, we're building an array of strings, and then we fold our array, and we end up with a SQL statement that looks like create or replace table, and then a list of the column names and their data types. So that's how we get our SQL database. Okay, and then the rest is pretty much very similar. We simply loop through all the rows that aren't the header. So we start at row 2, and we generate the SQL to insert that row into the database. But the key thing is really, once we have the SQL, we have to run it on the database server. So we call SQL execute. And we pass it our SQL, and it goes and executes this against the database. And once we've done that, we can have a look at the MariaDB database. which I have here. So this is MariaDB running on my machine. Here's our database, COVID. Here's our table that we created. You can see our columns, and we can see the data that we've inserted into our database. So we downloaded 1,416 lines in the CSV file, and we processed them, and we inserted them into MariaDB. Okay, great. So that's working with the SQL module for creating data. And now we need to look at our next data source. So statistics on relief funding for COVID-19. This again comes from the Centers for Disease Control and Prevention. It's a different data set though. This one is HHS Provider Relief Fund. And this one, unlike the previous one was available in CSV, Commerce Secretary. This one's in RDF, Resource Description format, which is a graph-based format. So this one isn't XML, well, isn't XML really. Again, there is an XML RDF representation, but this one is really RDF. So just like before, we're going to use the HTTP client. We're going to download the data, and we're going to store the data into the database. The reason being is that our database is RDF aware. So we can store our RDF document into the database, and the database will know what to do with it. Okay, so let's have a quick look at this. It's using many of the same concepts that we've just used. So it's not particularly complicated, this one. In fact, this is probably one of the simpler ones. Let's see. So again, we create a collection to hold our data. In this instance, our collection is called HHS Provider. We set that up earlier. And we download our RDF. Again, this builds the URI, sends the request across the web, checks the result and gets the data. So this returns our RDF. And then we simply store our RDF into a file in the database called HHS Provider RDF. And we've stored it in our collection. There's one extra step that the setup collection does here, whereas it defines an index for the data. So let me see, just here, what it does is it stores an index configuration document. And that document tells the database that this is RDF data and it should be indexed as RDF. And that's important for when we want to query it using Sparkle later. So here's our index definition that we stored. And it says, okay, everything that we store in this collection that is RDF should be indexed as RDF. Okay, and we can have a look at that data as well and see what that looks like. So let's have a quick look at that. The reason I'm not running these queries is because downloading some of this data takes a long time. This RDF data has something like 1 million triples in it, so it's not the smallest file. But here's our collection that we put our RDF data into. Let's look. Here's our RDF file. And if I open it up, hopefully this won't take too long. It's quite a big file, so we might need to give it a minute. But it will show us what's inside that RDF file. Okay. Well, we'll come back to that in just a moment because it can take quite a long time to load these files. I think this one's several hundred megabytes. So maybe opening it. Ah, here we are. So we can see our RDF data here, RDF, and we can see our literal values and properties and our resources here, of course. So there's our RDF all stored. Okay. Now that becomes a little bit more interesting when we start querying it. So, okay. We also need to map to and from state abbreviations and state names. For this, we took data from a website called the World Population Review. They also provide an API. And this one, the data is available in JSON. So far we've seen XML, CSV, RDF, and now we're also working with JSON. So this is very similar to the last one. We simply use the API via the EXPath HTTP from XQuery. It downloads the JSON documents, and we use the XMLDB module to store them into the database. So likewise, we can store the JSON straight into our database. And that one is here. I'm not going to show you the query because we don't have all that much time today, and it's very similar to the last one. If we look in here, we can see we've got some JSON documents. Okay, and these are the two that are query downloaded. Okay, so we now have the data, but how do we answer our question? Well, we have to actually query all of this wonderful data and figure out how to join it together to get the answers that we need. So first thing we want to do is query the death statistics. And the reason is that we're going to need to join these with the relief fund statistics. So we need to extract the information that we're interested in. Now, we've already examined the data. There's a screenshot here, but I showed you this in MariaDB earlier. We're going to use the SQL extension module, but this time, rather than inserting data into the database, we're going to pull the data back. And we're going to do this all from XQuery as before. So let's take a look at the simplest thing that we could get from this data using SQL and XQuery together. Oh, hold on. So just like before, we're going to use the SQL extension module. We make a connection to the database. For simplicity's sake, this time I've just hard-coded the parameters in here. Obviously, in better code or a larger application, you wouldn't do that. And then we're going to execute our SQL query against MariaDB. And this is simply our SQL query. Return everything from our table. So let's run that. Okay. So here's all of our data back from MariaDB. And because we're working in XQuery, the SQL module produces the results in an XML representation. So here's a row from the database. These are the columns. Here's the next row from the database. Here are the columns. I think you begin to get the idea. So each of these rows is a row from the database that's being pulled from MariaDB dynamically and then turned into an XML representation so you can work with it in XQuery. Okay, so let's do something a little bit more interesting because just getting all the data isn't really going to answer our question. So let's see, here we are. So here's our SQL this time. We're not just taking everything from the database. We're using SQL itself to do some calculations on the database. So what we want to do is we want to find the number of deaths in the USA per state. So we're interested in the location of things so that we can later determine if those locations are getting the same amount of funding proportionate to the amount of unfortunate COVID-19 mortalities. So I'm not going to explain all of this SQL code. This isn't really a talk on SQL, but needless to say, it gives us the information that we need. And again, we just connect to MariaDB. We execute our query. And then what we do is, given the XML back, we actually use a little bit more XQuery to iterate over the rows. And rather than getting our data like this, we turn it into a nicer form. I mean, nice is probably not the wrong word here when we're talking about depth, but perhaps a better format of the data. Okay, so let's execute this. So rather than seeing what we had before, we now see one of these for each state. So this one's for Connecticut, this one's for New York, New Jersey. We have the total number of deaths, and then we have the total number of those deaths that are related to COVID-19. And then we calculate using, that was done using SQL. We calculate a percentage, COVID percentage. So 32.57% of the total deaths were related to COVID-19. Okay, so we now have some data which is quite interesting about number of COVID-19 deaths and what percentage there are of total deaths within each state in the USA. And this goes on and on. Okay, So we've got the statistics that we need about death, and we've taken those from a SQL database. We put them into a SQL database, we queried them with SQL, we aggregated them with SQL, and we got the results back as XML. And we did all of this using XQuery. Okay. Now, the next one is obviously to find out the funding statistics. And first of all, we have to examine the data. I showed you the XML RDF earlier. Below, there's a little screenshot of the same thing expressed in Turtle syntax. Personally, I find Turtle easier to read than RDF XML. But this time, rather than using the SQL module, we're going to use the Sparkle module. So we can query our data with Sparkle. So let's see what that looks like. So here's, rather than a SQL query, we have a Sparkle query. This is a very, very simple query. It's simply going to return all of the states that happen to be in that RDF that we downloaded on relief fund statistics, fund payments. So if we run that, takes a moment or two. Okay, and we start getting back states, AK, that's Alaska, I think. And we can look through this and yeah, okay, we've got lots of states, CA, CT, CF, Florida. And this XML format that's coming back is actually part of the Sparkle spec. This is part of Sparkle protocol spec. So this isn't an XML format that we've invented. It's part of a W3C standard. Let's do something a little bit more interesting. So we can query the actual Sparkle payments that we want to get. So we want to know about payments made to each state for relief funding. So let's have a look at that. So the query itself, that's the Sparkle query. It gets a little bit more complicated, but this is still very just standard Sparkle. And we can execute it against our database using this extension function as before, Sparkle query. So let's run that. Okay, and here are the results. So we can see that Alaska, I think it's Alaska, received quite a lot in funding. What is that, 17 million odd US dollars. Oh, maybe AL is Alaska. Apologies to everybody from the US. Pretty sure CA is California, and we can see the payments there. So we can get some interesting data back from here. But what we might notice is that we've only got 10 results. We've got the first 10 states, yet we haven't asked Sparkle to only give us the first 10 results. So what's going on here? Well, nothing good, actually. This took me a bit of time to figure out late last night. And what I discovered is that, unfortunately, as of, well, yesterday, I guess, there's a bug in ExistDB's RDF Sparkle module where it doesn't return all of the data. That's not great, really, and needs to be resolved as soon as possible. However, you know, XQuery is very, very flexible. So I thought, great, there must be another way to solve this. So what I did is I downloaded a project called Apache Jenner, which has a Sparkle and RDF database. I loaded my data into Apache Jenner and set up Fuzeki, which gives me Sparkle over HTTP, which is part of the Sparkle protocol spec from the W3C. And because XQuery talks HTTP, as we've done earlier, to talk to lots of web things, I can just query the data directly from Jenner. So instead of querying it from Exist, I can query it from Jenner. So let's see what that looks like. Okay. Query Fuzeki Sparkle state payment. Yeah. So, oh, that's the wrong one. Apologies. So rather than talking to Exist and calling Sparkle query, we can instead build a URI and a web request that will hold our Sparkle. We can send our Sparkle to the Jenner Fuzeki server, check the results, just like we did with other requests that we made over the web, and get our results. So if we run this now, this isn't running the Sparkle against exist now, it's running it against Jennifer Zecchi. And we'll see that we have all of the states, which is great. And we can run our more complicated query. And what I've done is I've abstracted the talking to Zecchi into a little function called Zecchi query. So instead of calling Sparkle query, I can now instead call Zecchi query. And it's very, very similar to Sparkle query. It takes our Sparkle query and it's otherwise pretty much indistinguishable. So let's see what our query looks like instead. All states to, oh no, sorry. Let's get to the more interesting one. So at the bottom, rather than calling Sparkle query, call Zecchi query. This is the name of the data set in Zecchi. You have to give it a name. I'll just call it HHS, as that's our data. And here's our Sparkle query as before. So instead of Sparkle query, call Zecchi query. Okay, let's go. Great, so we're starting to get things back. We see AK, AL, we see the amount in US dollars. But this time, we're not limited to the first 10 states. We're seeing a lot more states, Texas, Virginia, Virgin Islands, Washington. Anyway, the good news is we can get all of our data and we still did it all from XQuery, so we're very, very happy. And let's see, right. Finally, we've got two data sets. The one that I just showed you though had, I'm sure you noticed, the abbreviations of the states rather than the names, whereas the defs data has the names of the states. So to join these together, we need to use our JSON mapping that we downloaded earlier. And the good news is that XQuery makes it very easy to work with JSON. So we can open this up. Query JSON state. So I've written two very small pieces of XQuery here. We call JSON doc to open up our JSON document from the database. And I've just chosen 3 state abbreviations at random. And we pass those state abbreviation functions, state abbreviations as parameters to our map, because our map, our JSON document map is really a function, because maps in XQuery are functions. And then I've just written a little example below, 3 different states, but by name. And this time we load the name abbreviation document, which gives us a JSON map in XQuery. And we look them up by passing the name to the map. So let's run this. And we see that given DE, it returns Delaware, given NY, it returns New York, CO, Colorado. And then below, given Idaho, it returns ID, given Nevada, it returns NV, et cetera, et cetera. So we have our mapping, and that's working quite nicely there. Okay. So we need to bring it all together. So we've written lots of little queries as we've gone, and we're going to use all of the components of those in one big query, basically, which is going to use each little part. And it's going to additionally calculate some percentages. And then it's going to iterate through the defs by state, joining it with the relief payments by state. And that join happens on the state name. Now, this is quite interesting because this query is basically taking data from SQL, joining it with data from RDF, and then, well, and that join happens by looking up data in JSON. So this query doesn't actually really work with any XML directly as a source anyway. So let's see what that looks like. And this will be our last query before I get on to some salient points. So let's have a quick look. And this one is probably for people to study later. So there's quite a lot in here. So if we start at the bottom, we quite simply, we get the defs. This is a function that we wrote earlier. We have a little function that calculates the percentage of them. This is our function that looked up. So this is coming from SQL, I should add. This is coming from RDF. This looks up our funding by state. We then look up our map for mapping abbreviation names. We modify the funding data so that instead of abbreviations, it has the full state names. We calculate some percentages of the funding data. And then we have a little XQuery here that iterates over the defs, finds the state of each def, the USA physical location state, I should add, then looks up the funding, which has the same state equals $state, and reports on it. So I'll just skim up briefly, but I'm getting a bit short on time. Here we go, total deaths by state. This is SQL here. It's being executed on our SQL database. And we're returning our tidied up XML. This is our query that we wrote earlier for querying the SQL data. This is our RDF-based query, Sparkle query, that we query for getting the funding information. And we're executing it on Fazeki query. And we're getting back the Sparkle protocol XML, and we're turning it into this format, payments. This is just as we did earlier. And then we have a couple of functions that expand some of this data, adding some additional things like total percentage of all, COVID-19 percentage of all. This is for deaths. We have payments, where we also calculate, oh, this is the one that expands the states. So there's our abbreviation map. We pass in the abbreviation, we get out the name. So we replace our state with the real name. This is the one for payments. This is the relief fundings. So we calculate the percentage of all for each relief funding. So we want to know if one state gets some funding, how is it as a percentage of all the funding that was given out? So if we run this, we should get our reports that we're looking for. This produces two reports. The first one is COVID-19 deaths by state as a percentage of all USA COVID-19 deaths. And the second one is relief funding payments by state as a percentage of all relief funding payments. So let's run it. Okay, so we can see that COVID-19 deaths by state, New York had the highest as a percentage of the USA at 11.5%. But did New York get the highest amount of funding? So let's look at our second report. So the first item here is New York. So New York received 11.5% of the total, 11.15% of the total relief funding. But these don't always add up. So New Jersey had 4.27% of total, I'm reading the wrong number, 11.98% of total COVID-19 deaths in the USA. But when we look at the funding, California, which had less total percentage of deaths, received more relief funding at some $4 billion. So it's quite interesting to see, and this is probably because I'm not a data scientist, that these things don't always line up. The states with the most amount of deaths or percentage of deaths don't necessarily have the highest percentage of funding to help with COVID-19. And there's one extra step from this, which is where rather than presenting the result as XML, we can present it as HTML, by using a little bit of XSLT to transform our XML into a HTML web page. And this uses the transform extension function. So if I run this one instead, we can get a nice HTML table with the things here. And if I open the result of this in my web browser, which I should be able to do, open data. This is the result of the XQuery that we've written that has combined the RDF, the SQL, the XML, and the JSON data all together to generate these tables side by side. So, for example, we see New York, again, highest percentage of deaths, but also received the highest percent relief funding. And some of these line up and some of them don't. For example, Illinois, it's in the same position within the table. So we think that's kind of proportionate. But California got a lot more funding, percentage-wise anyway, of the total US than the number of deaths that were there. But maybe because they got more funding, they had less deaths. Maybe they did better preventing it. I don't know. I'm not a data scientist. Okay, so I'm going to skip a couple of these, but hopefully I've demonstrated that you can do quite some amazing things with XQuery and a bit of XSLT and other things thrown in, but all driven from XQuery. So do we even need XProc? Well, yes and no. So we have so far managed to survive without it. It's not always pretty though. And if you are going to use XQuery, it's best to adopt some sort of compositional style. If you think about sort of monadic programming, that can be quite useful, creating lots and lots of small functional machines that can be glued together. And why did I even use XQuery? I mean, I could have written this in Java or C++ or anything that somebody suggested, really. The reason is XQuery is quite a good fit because of the XML data model and the ability for it to work over the web and tie in with other languages. So I do think really that we do need XProc because it has a cleaner separation of concerns. It's much, much easier for me to lay out small tasks and link them together. Whilst it can be done in XQuery, it can become a little bit daunting and a little bit kind of spaghetti-ish and hard to see the wood for the trees, dare I say. However, with XProc, I'd really like it if it ran inside the database. I want it to be as efficient as possible and exploit all of the advantages of the database. Maybe that's something we could think about in the future. Thank you very much. That's the end of my talk. So if there are any questions.
That's great, Adam. Thank you very much indeed. We do have a few questions. An anonymous one. When you say that your database is RDF aware, is that in reference to exist or to FusionDB, or I suppose both?
Okay. So when I said it's RDF aware, I was talking about both exist and FusionDB, but in the manner that I'm using the ExistDB RDF extension. And what that does is that adds a secondary index to exist, which is able to index RDF triples. And the Sparkle query call, the function call, is then able to use that triple index to answer Sparkle queries. For FusionDB, we actually want to develop a more native RDF solution rather than having a sort of extension module which is kind of bolted on. So.
Great, thank you. And Tom Hillman is asking, we would also like XProc in exist stroke FusionDB. Are there any plans?
It's really tempting to work on, but having seen Norm Walsh's and I've forgotten his, sorry, apologies. The chap behind Morgana, I'm sorry, his name's gone out of my head. Akin, thank you.
Yep.
Having seen Norman Akin's heroic efforts implementing XProc, I realized that it's no small, easy task. And at the moment, it's not on my critical roadmap. So whilst I would love to do it, I don't see me personally doing it anytime soon. That being said, if somebody wanted to do it or contribute, we would certainly try and support them.
It does sound like quite an undertaking. There's also a question from Alan Painter. I was going to unmute you, Alan, but I can't now see you in the list of attendees, so I guess you might have dropped off. Alan asks, I'm wondering why XSLT is not considered to be equivalent to XQuery in this proposition. Could it be because XQuery is often more associated with a database and you are using a database of intermediary results?
I think that's a very interesting question, and it's a very difficult one to answer, both technically and politically. Everything that I've shown, whilst I have stored, I've initially downloaded some of the data and stored it into Exist or stored it into MariaDB or into Apache Jenner, there's no reason why it had to be persisted. It could have stayed in memory. Perhaps it's easier to query with SQL if you put it into MariaDB, and it's easier to query with Sparkle if you put it into Jenner, obviously. But I mean, all of the things that I've shown from XQuery can be done from XSLT. My feeling is it's more stylistic. So when I don't know, maybe it's just how I write XSLT, but I very much write XSLT as a transformation from the input tree to the output tree. Whereas with XQuery, yes, of course, you can do an input tree to output tree transformation, but it is stylistically, it's more like a functional programming language. And so I find it easier to compose functional programs in XQuery. But yes, somebody could probably take this talk and rejig it into XSLT if they wanted. Having the database there is a bonus for sure. But this could probably be done without it. So I'm not sure if that answers Alan's question.
Okay, thank you. And Peter, I'm going to unmute you. You should be able to put your question now to Adam.
Hi, Adam. I'm writing, why not store the CSV results in XML documents rather than in an SQL database? Is there a performance reason not to use, or to use SQL?
No, not at all. I wanted to show that you could bring lots of different things together. So if I had downloaded the tabular data and converted it into XML, and I'd downloaded the RDF and converted it into XML, and the JSON and convert it into XML, I'd really just be showing that you can work with XML in XQuery. So I wanted to keep things in their native formats and show that you can still work with them without having to convert them into XML upfront. So I made it difficult for myself, I suppose, because I wanted to show the flexibility.
Fair enough.
Okay. I think that concludes the question and answer session. So it only remains to say thank you again very much, Adam. It was a hugely interesting and thought-provoking talk. Thanks everyone for coming. And we have, just to mention, we have one final session on this coming Monday, an XProc Q&A. Please do register if you haven't already. Thanks everyone, and enjoy the rest of your day.
Thank you, everybody, and thank you very much to Markup UK for having me.
Cheers, Adam.
Thanks. Good night.
Bye-bye.